Howdy, chemists. I know that redox reactions and half reactions are often problematic for us. If you're feeling that way about them, you're not alone. So I thought it might be useful if I did a problem and kind of tried to break it down in terms of steps. So let's imagine that I am trying to write the half reaction for the following chemical reaction. So we need a, come on, there we go, 4 aluminum, and it's solid, but I'm going to go ahead and leave that off just to kind of clean up our page a little bit. 3 oxygen gas. Oxygen's a diatomic element, so that. And then yields 2O3. So this would be aluminum oxide if you want to practice your naming. Okay, so my goal is to be able to write the half reactions to this. So I'm going to try to identify the steps as well as then kind of work through it. So first of all, what I would recommend as your very first thing, besides just kind of looking back and doing the like, what's being asked, what's going on. Okay, I see this represents neutral. This represents neutral. These are covalently bonded. Okay, here I see metal and a non-metal. So this is ionic. So if we go from neutral to ionic, that's a really good sign a redox reaction has happened because we don't create ions without the loss or gain of electrons typically. So I would do recommend a step 1, kind of a stepping back and asking what's going on in this problem? What does this chemical reaction represent? Next for a redox reaction is I would assign oxidation states. So assign oxidation states. And the reason I would do that is it helps me kind of even do what I was just talking about what's going on in the problem. What am I looking at here? So in order to do that, to change colors because I want to start with the single ladies rule or free elements, because if I don't, I might jump in, for example, right here and give this a -2, since that is often the oxidation state of oxygen. However, in this case, these are both representing free elements, meaning they're not ions and they're not in a compound. So to single lady, we put a ring on it. So they have oxidation states of 0. Now over here, they are no longer free ladies. They're married, they're in a compound. So I need to apply the other rules. So the oxidation state rule that's going to be the most helpful here is me recognizing that this is an ionic compound, which I can tell because it's that metal plus a non-metal. Aluminum is right on the edge of that boundary between metals and non-metals, but it is a metal, you know, aluminum foil, you probably know that. And then oxygen is a non-metal. So remember, the oxidation state of an ion is just its charge. And so you can often just use the periodic table and some of the techniques we've learned in the past for that. So for example, when I consider where oxygen is on the periodic table in group 16, I see it's, it's 2 spots away from the nearest noble gas. So oxygen has a -2 charge as an ion, so it has -2 as its oxidation state. Whereas aluminum, take a look at, if you have a periodic table handy, take a look at its location. It is in the same group with boron. So if you do the 1, 2, skip a few method to figure out its charge, all of the ones in group 1 have a charge of +1, all of the ones in group 2, and then we skip the transition metals because of their variable personalities when it comes to charge. And group 13, also known as 3A, tend to have a charge of +3. And so now I've assigned the oxidation steps of each and every element. And that can help me both in terms of figuring out how many electrons I need, and second, in terms of figuring out what was oxidized and what was reduced. So the second thing that I do when I do these half reactions is it's just going to sound really kind of like duh. I divide the reaction in half. Let me show you what I mean. Divide reaction in half. So I take the first thing, and if we could have been doing this very thing backwards. You have to be careful of getting in the habit of thinking every problem's going to look the same. If these two were together, I would just pull one of them down. So essentially, like, one of your either reactants, because we have 2 separate reactants, or if you have a compound that's decomposing, you're going to choose one of the elements of it. So choose one element that their oxidation state changed, so that it was reduced or oxidized, and bring it down and write, and I go ahead and bring the numbers down too, because we do need to have these balanced. So 4 aluminum, and then I do an arrow and I leave a little bit of room. And then I need to figure out what happened. Well, we already talked about how this became an ion. So I'm going to write that my neutral aluminum became an ion. And what's its charge? We just talked about it. So it became a 3+ ion. Remember, charges are implied when they're together like this in this ionic compound. But since I'm not going to be including oxygen in here at all, I need to have that +3, because if I just write Al yields Al, I don't understand what happened. That doesn't make any sense. Now, because I'm not bringing just the whole formula down, I'm going to move this 2 to the front, because remember what this 2 is reflecting? It's really just the ratio. So, but since I already have a 2, so 2 times 2 becomes 4. So 4 aluminum atoms became 4 aluminum ions. 4 aluminum atoms became 4 aluminum ions. 4 neutral atoms became 4 charged particles. Now, what happened to my oxygen? I'm going to do the same thing. I'm dividing my reaction in half. I do 3 oxygen molecules. Now, you might be confused as to why I didn't move that in front. Well, that's because these 2 oxygens are covalently bonded together. So now, if you made this a 6 oxygen atoms, that would be okay. I don't think that's necessarily wrong in this case, but we just don't do it that often, so I'm not going to do it. Yields, what do they become? 6 oxygen ions. So 6 oxygen atoms, or 3 oxygen molecules, became 6 oxygen ions. So I've divided the reaction in half. Next, I use my oxidation states from earlier to determine which is going to be redox and which is going to be reduction and which is oxidation. So determine R from O. So reduction from oxidation. And I shared with you guys how, so that I don't mix myself up, because it's just so easy to do because we've got all these backwards rules, I use these little oxidation hieroglyphics, or I jokingly call them white girl tattoos. So let's start with aluminum. Aluminum's oxidation went from 0 to 3. So if I think vertical number line, here's my number line, here's 0, going up to 3, that's going up. Therefore, aluminum was oxidized. So I'm going to put an O here or an OX or something to clarify. That way I label and identify that this is my oxidation. Now I know automatically now this must be my reduction. But we're going to go ahead and double check. Oxygen went from 0 down to 2, a decrease in oxidation state. So that does represent reduction. So from there, I place electrons on the appropriate side of the arrow. So how can we simplify that? Place electrons on right or left side of the yield sign. Remember, we don't use equal signs for reactions, yield sign. So how do I know right or left? Well, if it's oxidation, that means loss, right? Oil rig. So if it's oxidation, I put them on the other side as a product. Now, I still use a plus sign. No minus signs. No, no, no. So oxidation is loss of electrons. That's how a neutral atom becomes positive, by losing these negative charges. So I put electrons on the negative, or on the product side for oxidation, and I put them, I didn't leave myself as much room as I should, on the reactant side for reduction. Because how does oxygen become an oxygen ion, a negative oxygen anion? By gaining electrons. So I place electrons. Notice I didn't say anything about number, because that's my next step. I'm going to determine the correct number of electrons. So I just put the electrons there, but I didn't take it into any account. And there's 2 things we have to consider. First, we want to consider how many places the oxidation state moved. How many places the oxidation number moved or changed. So for aluminum, it changed by 3, because every one of those movements from 0 to +1 to +2 to +3 right here, each of these represents an electron. So that means for aluminum, 3 electrons. However, I also need to consider the balanced equation. Consider the number of atoms that were involved in this, or ions. So consider the balancing of the equation. Maybe I'll put that balanced equation. So every aluminum atom lost 3, each of them, so 3 electrons. But notice how many there are. There's 4 of them. And if you have 4 atoms, each losing 3 electrons, that's 12. 12 electrons. So from this, we're going to determine the correct number based on how many places the oxidation state moved and the number of the coefficients involved in the balanced chemical equation. Now we need to do the same thing for oxygen. These two numbers should be equal, however. If they're not, there's something wrong with your thinking or maybe what you've written down and you need to relook. But you should double check it to make sure it makes sense. We're going to do the same thing though. How many places did oxidation move? It moved 2 places. So that means each of these oxygens gained 2 electrons. But how many total oxygen atoms do we have involved? Well, we have 3. Remember that here's our oxygen's Lewis structure. There's a molecule of oxygen. That's what that O2 is representing. And we're going to break that bond with the addition of these electrons, and that's what's going to make then the Lewis structure of oxygen ion, just so we can visualize what's going on here. But we do this a total of 6 times. So 3 of these makes a total of 6 of these. So 6 times 2, 12. So, and then our final step should always be to kind of look back and ask ourselves if that makes sense. So, are we good? Makes sense? One of the ways I like to do this is to kind of go back through and see what I've represented. Okay, I had neutral. That means number of protons equals number of electrons. The reason I know it's neutral is there's no charge and there's no information to otherwise imply it's charged. How does a neutral metal become positive? By losing negative charges. Do my numbers make sense? Do they match up? Are my electrons, this is kind of important, are my electrons on the opposite side for the 2 reactions? That's another way to check your work. So notice that on this side, they're to the right of the yield arrow, and on this side, they're to the left, so they should be opposites. Do they match in number? If I kind of put it back together, would it make the whole reaction? So those are all some ways you can check your work. And hopefully you've seen that there's extra practice on assigning oxidation and writing half reactions on Canvas. So continue to let me know if you have questions or concerns.